Hello, Math 3 students. Welcome to Unit 1, Day 4, Centers of Triangles. I'm going a little off the cuff here. I'm not going to be writing on specific examples, but I'm just going to talk to you about the general properties about different segments that meet in triangles, maybe show you a couple pictures and animations that help solidify some of the definitions and theorems about them. So I'm just going to kind of draw a couple pictures for you to start. So if you draw a triangle, and I'm going to use straight lines and cheat a little bit, what we would do, if I had it doesn't have to be isosceles or equal out. If I just had a triangle with three sides, say like that. And if I were to draw a segment inside the triangle such that it hit the vertex of the triangle in the midpoint, and I'm just going to kind of eyeball that, about right there, the midpoint of that side of the triangle. So in other words, it cut that in half. This segment's called a median. And I can draw that for all three vertices of the triangle. Now it turns out that if I draw three of them, and if I do this accurately, they're all going to cross in the same spot. So if these two are the same, these two are the same, and these two segments are the same, about the best I can do. These all three segments are called a median. The point that they intersect at, we call that the centroid. So you kind of hear, centroid and median kind of sound the same. They both mean, middle, I guess. But the medians are the segments connecting the vertex and the midpoint of the opposite side. Centroid is the point where they meet. Now, the cool thing about the centroid properties is it's always going to be inside the triangle. So if you look at this animation here, no matter how I change the triangle, that centroid will be inside. It's always going to meet there. I could move these other vertices and it's still going to be in there. And the cool feature about the segments is that the centroid is actually 2/3 of the way across the median. So this segment right here, let's say this segment is 8. All right, let's say this is 8. Well, if that's 8, then 8 is 2/3 of what number? Well, what's half of 8? 4. So if I add the 8 and 4, that whole segment's going to be 12. So 8 is 2/3 of 12. 4 is 1/3 of 12. And then 8 is twice as much as 4. In fact, that relationship's going to exist, and it doesn't matter what the segment is. I could just call it x. If this is x, this will be twice as long, and the whole median will be 3 times as long as that little guy, or this is 2/3 of that whole thing. So a very special property, and that centroid is also the center of balance of that triangle. So you could balance that thing, and it would stay put. If you had a piece of cardboard or something sturdy and you put a pencil tip right on there, it would balance. It wouldn't fall off if you drew that correctly. So that's a median and centroid. Of course, remember that medians intersect at the vertex and the midpoint of the opposite side. So these two segments are the same length as well. All right, moving on, doing a different example. Let's talk about angle bisectors. So instead of cutting in half the side, if I were to cut in half the angle, Okay, so I'm going to estimate this. So such that these two angles are roughly the same measure, or exactly for that matter. These two angles are exactly the same measure, and these two are exactly the same measure. Now, they're not going to hit the midpoints of the sides, but what's going to happen is this angle right here is congruent to that angle. These two angles are congruent to each other, and these two angles are congruent to each other. Okay, this is called an angle bisector. You'll notice that they are concurrent. In other words, they all three meet at the same point. That point's called the incenter. Okay. Now, why is it called an incenter? Well, first, to understand what that means, you have to understand a little bit about what an angle bisector does. And an angle bisector ends up giving you this segment right here is the same distance from the sides of the angle. We call that equidistant if you go at a right angle. So if I go straight down to the side at a 90-degree angle, let me do that in blue. This segment right here if I drew this perfectly, would be the exact same measure as this segment. It would be the exact same measure of this segment. Now, in my opinion, these are the hardest ones to draw. So I didn't get it right on the mark, but all three of these are the same. And so this point is equidistant. We call that equidistant from the sides of the triangle. Now, why is it called an incenter? Well, because I can draw we call an inscribed circle, which is the largest circle that can be drawn inside of a figure. So inside of the triangle, that ends up being the center of that circle. So it's in the center of the circle. And the equidistant segments are basically a radius of that circle. Okay, so that serves as basically the radius of the circle. You get the area of the circle if you wanted to. So these two angles are the same. These two are the same. These two are the same. And the radius, or this point inside or to the side of the circle, are the same. Let me show you a little bit of a animation for that. All right, so here's a picture of a triangle with, we call this an in circle. This circle is the incenter of that triangle. These two angles are congruent. These two are congruent. And these two are congruent at C. But you notice that point is always inside the triangle, no matter where I draw it. Okay? So, moving on. All right, so another special segment in a triangle is called a perpendicular bisector. Now, perpendicular means intersect at 90 degrees. Bisect means to cut in two congruent segments. So, let me type that on here. A perpendicular bisector might look like this. If I go about halfway to, use a different color, about halfway across one side at a right angle, it doesn't necessarily have to touch the vertex. In fact, a lot of times it won't touch the vertex. But if it looks like it's at a right angle, it's perpendicular, and it's cutting that side in half. So it's a perpendicular bisector. all three perpendicular bisectors will meet. Okay. Let me make a couple marks on here before I move on. So these two are congruent. These are congruent. And they will meet at a point. That point has a special name as well. That's called the circumcenter. Now, the reason it's called a circumcenter, the other one was an incenter for an angle bisector. The circumcenter is actually the center of a circle going around the triangle. So if I draw a circle, we call it circumscribing the triangle. And I'm not the best at drawing these, but I'll do what I can. All right, so each of these vertices of the triangle can hit the circle. Any triangle you can do this with. And what happens is the segment that if I connect to the circle, sorry, my train of thought kind of got lost. But if I connect from the circumcenter to the vertex, all three represent a radius of that circle, okay? They're all going to be congruent. So these three lengths are the same. So if this is 20, that's 20, that's 20. And again, these are cut in half. That's a 90-degree angle. Now, let me show you a little animation. So if you construct three perpendicular bisectors, or really you can do it with two, but with three of them, they'll all meet at the same point. And you'll notice that I can change the vertices around. And if that triangle's acute, if all the angles are less than 90, that point's going to be inside the triangle. Now, if I make that triangle a right triangle, you'll notice that that circumcenter ends up being along the hypotenuse. In fact, that's halfway between in the hypotenuse. So it's the midpoint of the hypotenuse. Look at angle B now. Angle B is obtuse. What happened to the circumcenter? It went outside the triangle. So again, when it's a right triangle, it's in the center of the hypotenuse. When it's an acute triangle, it's going to be inside, but it's always the center of a circle going around that triangle. That's why it's called the circumcenter. Center of a circle, circumscribing the triangle. All right, the last segment we'll talk about is an altitude. And I'm just going to hand draw this. An altitude's a height. Height has to go from the vertex to the opposite side at a right angle. No special relationship for the lengths. If I were to rotate this around, the height would look something like that. And this height would look like that. If I were to draw this perfectly, again, these would meet at the same spot. We call that spot the orthocenter. The reason it's called the orthocenter is, well, it's orthogonal means intersecting at right angles. So that's where the ortho part comes from. So the altitude is the height. Orthocenter is where they meet. They're going to make right angles. There's not really a lot more to it than that, other than the fact that the orthocenter like the circumcenter, can be inside the triangle if it's acute. It could be on the triangle. In this case, look at it went to the right angle in the triangle if it's a right triangle. If it's obtuse, it's going to go outside that triangle. So just kind of follow where it goes. Again, we don't really have a special relationship about the lengths. It more or less is just dealing with 90-degree angles for that. And again, inside the triangle if it's acute, on the right angle if it's a right triangle, and outside if it's obtuse. There's a right triangle, it's on there, inside, on, and out. So there you have it. Hopefully that was helpful for you. Again, everything that I discussed in the video is pretty much summarized in this graphic organizer that I handed to you. It's not going to help you necessarily solve all the problems, but at least gives you a start to find some information, and it should give you enough stuff to be able to do most of the day for assignment. So hopefully that helps you, and thanks for listening. If you have any questions, let me know.